buying a big bag of chips, only to open it and find it's half full of air. Disappointing, right? You paid for the whole bag, but only part of it was useful. That's exactly what happens in our power systems when we talk about power factor. So, what does a power factor mean? Power factor is the ratio of real power to apparent power. Real power is the actual chips, the part that does the work, the appliances that do useful work. Reactive power is the air in the bag. It doesn't do useful work, but it still takes up space in the system. Apparent power is the full bag, or the total power delivered. So, power factor is equal to real power over apparent power. The closer it is to 1, the more efficient your system is. A low power factor is like paying for a bag that's mostly air. You're not getting what you paid for. When power factor is low, costs go up. Utilities may charge extra fees for inefficiency. Systems wear out faster as more current flows than necessary, which overheats wires and causes voltage drops. We can visualize this using the power triangle. It's based on the cosine of the angle between real power and apparent power. If the angle is 0, the power factor is equal to 1, and all the power is useful. If there's more reactive power, the angle gets bigger and power factor drops below 1. How do we fix a low power factor? There are 3 main components in an AC circuit: resistor, capacitor, and inductor. These can affect the relationship between current and voltage waveforms, and thus, power factor. We try to get current and voltage back in step with each other. If current is lagging, late, we add capacitors. If current is leading, early, we add inductors. This makes the system more efficient, like making sure the bag you bought is filled with chips, not just air. Certain waveforms result from these effects and have differing features. For example, a pure resistive waveform sees the maximum, minimum, and x-intercepts aligning when the power factor is equal to 1. For a pure inductive waveform, the maximum, minimum, and x-intercept of the current wave are reached 90 degrees after the voltage. This portrays a lagging power factor. Finally, a pure capacitive waveform sees the maximum, minimum, and power factor of the current wave reach 90 degrees before the voltage. Thus, a leading power factor on a big scale. When lots of machines run with a poor power factor, the whole electrical grid must work harder. That means more current, more heat, and more strain on equipment, and higher costs. Since utilities may charge penalties for wasting power by correcting power factor, we save energy, reduce bills, and make the entire power network more reliable.